Welcome back to the second lecture of the week. And this week, or this lecture, we want to more concentrate on this notion how the subgroups will influence the behavior of the random walks. So I need to revise a little bit of some basic things about group theory. But the basic idea in this lecture will be about this notion of non-concentration of random walks into subgroups, and especially something called cosets of subgroups. And here we will use these notions of sumsets that we had in the earlier lecture, and we will also talk about kind of how the random walk is connected by the support of the driving probability distribution to these kind of additive structures that we are going to be using. So a couple of revisions that, if you remember, so let's go to the non-concentration of random walks. So even though it's more about random walks, it's really be more topic on about the subgroups. So if you remember, a subset, let's call it gamma, in ZB is a subgroup if this kind of condition holds, so T plus S. So it's closed in the addition. And then the other thing that we use here, of course, is the, we say that this gamma, so maybe we actually write this gamma in ZB, if it's a subgroup. And then this gamma ZB is trivial if this gamma is equal to the identity element, so the 0, and then we call gamma ZB is proper if gamma is not equal to the whole ZB. So it's kind of like a trivial and proper subgroups are the kind of non-trivial and proper subgroups are the ones kind of what we would be interested of. And then the one thing is also that if A is a subset of ZB, then A generates some gamma, let's call it gamma subset ZB if the subgroup generated by A is equal to ZB. So that's one final thing. And then this kind of like notion of cosets. So a subset, let's call it C in ZB is a coset of a subgroup gamma if there exists T in ZB such that this C can be written as gamma plus T, where this is the sumset notation, so this gamma plus T is just equal to the, let's call it A plus T, where A belongs to the subgroup. So these are the kind of fundamental notions that we want to consider. Of course, like if you remember that the group ZB, it's actually very simple. So the subgroups are usually given by the kind of singletons or unions of the singletons. And there's like a, for example, when you have a prime number P, then the only there's actually no the only things that there are trivial subgroups or the whole subgroup itself. But in some cases, you can have like some non-trivial situations. So let's call it non-trivial situations are like, let's say, Z4. So for example, here you could take 0, 2, that's a subgroup, and then you could have a coset. So let's say 1 and 3, this is a coset of this 0, 2, because you can basically add 1 into this situation. So the kind of non-concentration idea is that that if you start adding these elements together, so if you start adding like these subsets together, then you might have this kind of like a idea that after some point that you started adding these sets together, you end up to the whole group, unless you are in a subgroup or like possibly a coset of a subgroup where you have this. So there's this lemma, which is, I think in the lecture notes, this is lemma 3.29, which is the following, that let A be a subset in ZP, any subset. So if A is not contained in a coset of a proper subgroup of ZP, then there exists n in N such that when you take this set n times, so I use this kind of notation, A plus N, this is N times, then this is equal to ZP. So any subset, so this has nothing to do with random walks yet, we just take any subset of ZP, and if we start adding it together, and as long as it's not contained in a coset of a proper subgroup, so this coset of a proper subgroup of ZP is the main condition, that it's not contained in this set, not contained in a coset of a proper subgroup in ZP, then we have this notion. So the it's very important. This is the kind of like what you will later see, that when you apply this to supports of these probability distributions, this really connects to the convolution of the random walk and gives you like a connection to the group theory. So I give you the proof. So the proof is on the notes, but I'll go through it like briefly, like the main ideas of the proof. So it uses this kind of first property, what we have in the notion. So it's like a sublemma that if A and B are non-empty and this cardinality of the sum is equal to A is equal to B, then A and B are cosets of the same subgroup gamma in ZP. So that's kind of the first main property that we prove. So this kind of sublemma that if you take any two subsets, which are non-empty, and the cardinality of their sum set, so A and B, when you sum them together, actually equals to A and B. So if you remember about the sum sets, like if you go to the lecture when we talked about the sum sets, typically it's very common that the sum sets, it adds the cardinality, it increases. But here you basically don't have any increase. Then you can actually say that if they don't increase cardinality, if you add them together, you just get nothing more, then you have a coset of the same subgroup. So if you just a quick example, like if you take A equals 0, 2, let's say non-empty, and maybe b is equal to well, I could just take the same, that if they are the same sets, for example, then a plus b is equal to just 0, 2. So of course these are the same, but I could take, for example, maybe I take the this example 3, and these are all a and b in Z4. So if I take them in Z4, then their sum set is equal to 1, 3. Wait. Maybe actually the better is the 0. Okay, so if you take the example a equal 0, 2, and also b, then of course in this case a plus b is equal to 2, which is well, it's the cardinality of 0, 2, which is equal to 2, which is then equal to the cardinality of a, cardinality of b. So that's the kind of main kind of lemma that we want to prove first. So how do we then apply this lemma? So before I prove this, I'll give you the kind of application of this. So so using this sublemma, we get the following, that if a, so now we just come into the claim of the theorem, if a is not contained in a coset of a proper subgroup of well, it's just a coset of a proper subgroup. Let's assume that this first, that it's this case, that it's not contained in a coset of a proper subgroup. Then this implies that neither is a plus n for any n in n. So before going to the cosets, then if you add the sum to itself, so if you have this, that a is not contained in a proper subgroup, so this is never contained in a subgroup, and this would be a subgroup, then of course the big sum can never be either contained in the same subgroup, because if it was, then you could actually extract that the A itself would be contained in a coset of a proper subgroup. So this is a plus T subgroup. So if you use this property, what we just said here, then what we get from this lemma that we have obtained is that if we apply this in the situation of A and A itself, so first of all we get A plus 2. So now using this we get first of all that A plus 2, if you get this is A plus A. So now if you apply this, then this has to be bigger than A. Because if you look at the sublemma, what it said here, that if A and B are non-empty, okay, so we have a non-empty set, let's say we assume that A is non-empty, and A plus B is equal to their sum, that they are cosets of the same subgroup. So here you're using the same set A, so this has to be bigger than that, so there has to be some increase. And now using this again, then what we have here 2, we have A plus 3, which is now A plus 2. So now this is your set B that you want to apply to, and then it has to be also bigger than the A plus 2. And because now we are applying again with the same thing, and then we have the same, then a plus 4 is a plus 3, then this is bigger than a plus 3, and so on. So it has to always increase with this property. So in general, we will have this increase that for any n in n, if you take a plus n, then it has to be bigger than a plus n minus 1. So it's an increasing sequence, these cardinalities that we have here. So this a plus n is increasing, well, is strictly increasing in n. Well, the problem here is that if it's a strictly increasing, we have an upper bound. On the other hand, we have that this a plus n has to be at most p, as it's always a subset of the subgroup. So because it's a group, then it's always a subgroup. Well, it's a subset of the elements. So there's only p numbers in there. So that means that there exists an n in n, that this actually increases because it's strictly increasing sequence. So it has to imply that there exists an n such that this is equal to ZP. Well, you could say that this is equal to the sum, which means that there exists an n such that a plus n is equal to ZP. Okay, so in order to prove the sublemma, if you want to get into the situation, so the proving this main statement, then I'll show you it now. So this is the half of the proof. So and then proof of the sublemma. We can do it as follows. So what we are claiming here is that we have two non-empty subsets with this property, and then we want to prove that it's the coset of the same subgroup. So what we can do here, we can take T and S in, well, actually let's take T in A and then and S in B, so any general elements, and define A prime to be equal to A minus T and B prime B minus S. So we translate them. Let's draw the picture. So we have some set, let's say here, let's put it, let's say 8 elements here. And we could have like some set here and then maybe another one in here. And then we translate them so that, let's say if this is T and this is S, then we kind of translate them back into getting the, actually here this goes back into origin, minus T, and then this is minus S. So we translate them back so that then the sets kind of begin from the origin. Okay, so the reason we want to do this is that now when you compute the sum set of these A prime plus B prime, you will actually obtain that this is equal to A plus B plus T plus S. I think that's the way you get both of them if you compute their sum. Yes, so if you take the subtract, yeah, I think that's the case. Maybe it's minus A plus B. Might be the minus actually on the K. It doesn't really matter which one you get from the thing, because now the the main important thing is that the cardinality of A plus B is actually the same as A plus B, and by the assumption, this is the assumption, this is equal to A, which is equal to B, but that's actually equal to A prime, which is equal to B prime, because of the sum. It's just basically a translation of the original set. And and now note that we have the following property, that 0, which is t minus t, this belongs to A prime, and 0, which is also s minus s, this belongs to B prime. So we have this kind of 0, we did this translation to 0, and the reason we wanted to do this is that when we take the A prime over here, so now the A prime contains, for example, sum, then this also belongs to A prime plus B prime, and B prime belongs to A prime plus B prime. So this is kind of like just because the 0 is inside the sum set. So thus, because now it contains the set and they have the same cardinality, so remember that the sum set has the same cardinalities as the original set, and it contains the original set, just by the cardinality similarity cardinality property that A prime plus B prime is equal to A prime equal to B prime. We obtain that A prime plus B prime is equal to A prime is equal to B prime. It's just they have to be the same at this property. I could write them this way. So they have to be the same sets. So in particular, because they are the same sets, A and B prime have to be the same. So we have obtained that A prime plus A prime has to be A prime, which then implies that in order for something like this to happen, this implies that A prime is a subgroup of gamma. So this implies that, but we know that this A prime, this was equal to, if you remember from the beginning, A prime was a translate of A, so this is A prime minus T, so this would be subgroup of ZP, so A so A and B are cosets of the same subgroup, because now this is the same, this is A and this is B prime, they both are subgroups, and this is B minus S. So they are both cosets of the same subgroup, and that's the claim we wanted to do. Okay, and the reason why we wanted to do this lemma, so now this is like the end of the proof, was that we want to talk about the non-concentration. And in the next lecture, I will go into how this actually helps with the non-concentration for the subgroups. So I will talk about something called ergodic theorem. And for that purpose, the motivation why we wanted to do this is this theorem. Let's call it theorem 3.30 in the notes, which is the following, that we let mu be a probability distribution, and then this support of mu, if you remember, is not contained in a coset of a proper subgroup of ZP if and only if there exists an n in n such that the support of mu star n is equal to ZP. So this will be basically a consequence of the previous property that we had, but I will come into this in the next lecture. So this was basically the kind of motivation why we wanted to do this. You can probably already see how this is related to the original thing, but I'll come into this again in the next lecture. So thank you.